So we're talking about changes that occur to the sun. And some of these changes that occur on the sun originate in the core. So let's talk about the core again. Remember, we got the proton-proton chain. And we've explained how the proton-proton chain works. Now, the thing that I should also point out is that's not the only proton-proton chain. The regular proton-proton chain, what we call PP1, is the hydrogens fuse and they make a deuterium. Okay, the deuterium fuses, makes a helium-3. The helium-3s fuse and give you back a helium-4 and then 2 leftover hydrogen. This is your generic proton-proton chain. This dominates in the sun. But there's another proton-proton chain called the PP2 branch that also happens. Instead of that helium-3 fusing another helium-3, it can actually fuse directly with a helium-4 and make a beryllium-7. The beryllium-7 can then actually do what's called an inverse beta decay, and that is capture an electron, undergo a nuclear reaction that then creates a lithium plus a neutrino. The lithium can then fuse with a hydrogen and makes 2 heliums. In fact, this step right here, lithium fusing with hydrogen, is super easy to do. That step actually takes a lot less energy, it's a lot less difficult to do than actually fusing the regular proton-proton chain. And so that's why that process was used in the very first hydrogen bomb, is that lithium and hydrogen will fuse with very less energy. In fact, almost any lithium in even a protostar is going to fuse simply because the protostar itself is going to be hot enough to get this done. Okay, but this process of fusing this step right up here starts to dominate if the temperature in the sun gets high enough. Now, right now, it's pretty hot inside the center of the sun, but it's gradually getting hotter as the core is shrinking. Remember the previous lecture. And so once it reaches 14 million Kelvin, then it becomes, this proton-proton 2 chain actually begins to dominate. And of course, at that point, you got so much of this helium-4 in there that it starts to really step up. Okay. Proton-proton 3 chain actually really starts to dominate at a later time. And what will happen here is that the beryllium, instead of doing an electron capture, inverse beta decay, if it bumps into another hydrogen, it will fuse into a boron. The boron then emits a positron and becomes beryllium, and the beryllium splits into two heliums, rather. Okay, so I'm not going to make you memorize these other proton-proton chains, but I do want you to know that there are other things that happen nuclear fusion-wise inside the sun. It's not all just what we said before. There are other things that are happening in here, because this plays out later when we discuss how stars evolve. Right now, about 86% of the fusion inside the sun is proton-proton 1, and about 14% is proton-proton 2. A fairly negligible amount is proton-proton 3. Now, as the sun gets older and the core gets hotter, what's going to happen is that the amount of proton-proton 1 is going to decrease, and the amount of proton-proton 2 is going to increase, and then you're going to start getting an appreciable amount of proton-proton 3. Now, it's never going to completely transition to these other layers because eventually you're going to run out of hydrogen to fuse in the first place. Okay, so another thing that happens is that once the temperature gets over 15 million Kelvin, another cycle starts in, something called the CNO cycle. The CNO cycle is another fusion process in which you start with a carbon. The carbon fuses with a hydrogen, and that gives you nitrogen 13. The nitrogen-13 then will fuse with another hydrogen, and that gives you carbon-13. Okay, that carbon-13 will then fuse with another one, give you nitrogen-14. Okay, sorry, the carbon-13 becomes nitrogen-13. Okay, the nitrogen-13 fuses, gives you carbon-13, which fuses, gives you nitrogen, gives you oxygen-15. The oxygen-15 then fuses, gives you nitrogen-15, spits off a positron and neutrino. The positron and neutrino being spit off here too, and then a big chunk of this breaks off and becomes a helium and gets you back to the original carbon-12, and then you repeat the whole process again. So this is called the CNO cycle. The CNO cycle starts dominating inside the sun once the temperature gets very high. Now, it starts originally, you have to get above 15 million Kelvin to even start doing this, and you have to have carbon in there to begin with. There's not a whole lot of carbon in the sun, just barely enough to get this happening. But as this core of the sun gets hotter and hotter, it starts switching more and more to the CNO cycle. Okay. Now, why is this interesting to us? Well, because all these different cycles also produce neutrinos, but they produce neutrinos with different energies. So that means if you were in an advanced civilization on a planet orbiting a star, you could actually measure the neutrino energies coming out, and from that you could figure out where in the life cycle your star is. The sun starts doing the CNO cycle quite late in its life. And so that would be a clue that it's about to actually die. Okay. So here's kind of a graphic that shows the CNO cycle from one step to the other. Again, spitting things out, becoming one thing and another thing, and so forth. And then as it spits things out, it changes, and then it goes back to the way it was. Okay, so that's the CNO cycle. Eventually, though, the sun's going to run out of hydrogen in the center of it. And so all of these hydrogen fusing cycles stops. So that means all three of the PP chains stop. The CNO cycle stops, right in the center of the sun because there's no hydrogen left to fuse. Okay. Now, at that point, the sun's truly dying. Okay. But long before it dies, it's getting old. And as it gets old, that's going to impact Earth in a negative fashion. The sun will eventually run out of hydrogen. Depending on who you ask, it's 5 to 7 billion years. About 5 billion years, you're going to run out of hydrogen in the middle of the sun, but you're still fusing some hydrogen in the outer parts of the core out here, so you're not totally out of it. So some give the life of the sun as maybe another 6 billion years, and then there's some indication there'll be a little bit of convection and turbulence bringing some hydrogen from the outer layers down into the core. If that happens, that can add another billion years, and so maybe up to 7 billion years. Earth does not have 5 to 7 billion years left. The sun does. But in only 1.5 billion years, the sun's going to be 15% brighter than it is now. And at that point, there's going to be a greenhouse effect. Just water, oceans are going to be, water is going to hold in heat on Earth. And so the temperature of the Earth will get so high that most current life forms, trees, grass, most animals, including humans, will die. We're not going to be able to survive. Within about 3.5 billion years, long before the 5 to 7 billion years the sun takes to die, in about 3.5 billion years, the sun will be bright enough that the oceans will boil away and Earth will be this big desiccated, dry thing, kind of like West Texas. And so this is the future of the Earth long before the sun dies. And so the sun is gradually changing, and long before it dies, we're not going to be able to live here. The important part of this, though, is that only the core is doing the fusing, and only the core is running out of hydrogen. The outer parts of the sun still stay mostly hydrogen and some helium. That unless you get a whole bunch of turbulence and mixing, they don't change.